It's probably not surprising for you that during the time, the amount of data grows almost exponentially. And with, say, Internet of Things and more devices connected to the Internet, we can be pretty sure that this trends will continue, and probably in a couple of years, the amount of data being generated on the Internet will again grow exponentially. This is probably not surprising. What is maybe a little bit more interesting is structure of the data. The black part, which grows linearly, is rough estimation that this part is formed by structured data. But this exponential part is mostly created by semi-structured or unstructured data. This has some implication, and I will return to this a little bit later. But I guess this amount of data is really big, and this phenomenon is known as a big data. So maybe, for everyone it can mean something different. So maybe to be sure that we are on the same page, how big the data has to be to call it big data. So do you have some definitions, or how big the data have to be to call it big data? So some more tips. I have scarf, I have half full bottle of cola if you don't want scarves, or banana. So terabytes, okay, terabytes. Somebody else? No? 1 megabyte? Okay. So some definitions. Okay, so probably the most popular and commonly used definition is this one, that big data is anything which carries your Excel. It's kind of joke, but we can take something from this, and that is that basically you can buy more beefy machine, you can buy a recent version of Excel which support more rows, but with this exponential growth, sooner or later you will probably, the scaling up won't be sufficient, and you will probably have to scale out. And this scale out and scalability issue is not always just because of amount of data, but also because of cost efficiency. For example, imagine you run a shop on the internet, and before the Christmas you probably have to deal with really a huge amount of data, while during the summer when everybody is on the holidays, the amount of orders will be probably significantly slower. So there's no point to buy some really beefy, big machine just before 2 weeks before the Christmas, and the rest of the year have this beefy machine. So there are two main reasons: just amount of data, and not only this, but cost effectiveness. Some other challenges of big data. This is not completely, there are a couple of challenges which I will try to address later in this talk. So if you have a huge amount of data, of course, running an analysis on top of that is challenging, just because of a huge amount of data. You have to also store somewhere the data. And as I mentioned in the first slide, quite a lot of data can be unstructured. So you have to have some solution which is able to store the unstructured data, or not process data which are not processed. Again, there can be other reasons, like that the data have some structure, but you are not able to process them, and just for performance reason you store it as they come and process them later. And when you run some analysis on top of that, you probably will get some data which has some better structure, and which you will probably want to later on run some queries on top of them. So you probably also need some solution which is able to store some structured data and run some queries on top of that. So quite often you need both store unstructured data and as well as structured data. The solution, as I mentioned, has to be scalable. and the scalability is usually done in the cloud. But running application in the cloud gives some more challenges because it completely changes the architecture of the application. In the cloud, everything is ephemeral, so applications have to deal with the fact that some piece of hardware will die, and application will have to live with that. So can't rely that I will store the data here and 2 days later the data will be there. So it changes also the approaches how we create the application. So probably the most widely used approaches how to address this kind of challenges is data replication and then running some MapReduce on top of this data. And probably the most popular solution is Hadoop. So far, so good, I would say. I just recap some probably well-known facts, which you probably know. So are there any Hadoop users or who run or at least play with that? So are you happy with Hadoop or something? So it seems everything's okay, so why Hadoop is not good enough? What doesn't make you that you are not completely satisfied with Hadoop? Nobody? So, well, you know, people today are more and more impatient and want their answers immediately, you know. Nobody sends letters, everybody sends email, or some people even make phone calls and want to have some communication in real time. So for some people, it's slow, because you store some data in Hadoop FS, and for example, once a day, run some analysis on top of that, and some people may, and with the analysis take pretty long time, so some people seems want to do it faster. So how we can speed the whole process up? So one really powerful idea is, especially for algorithms which are iterative, don't store the data to Hadoop FS or to some permanent storage. During the computation, keep the data in memory all the time. And as I said, you remember that you run it in a cloud. So it has some implication. You are replicating the data, you run some transformation on top of the data, and if you store it, it will also get replicated. And again, it takes time. So maybe stop and think a little bit, do I have to replicate every single change? And the answer would be probably no. Maybe I can run some bunch of operation and then replicate the result set. So it's easy to say, maybe a little bit more hard to do. But fortunately, there are some frameworks which already does that, and probably the most popular one is Apache Spark. In the heart of Apache Spark is a concept which is called resilient distributed data sets, and the shortcut is RDD. It's basically immutable distributed collection of data. Immutable, it means that if you run some change on top of that, it doesn't change this RDD, but it creates new RDD. And there are basically two kinds of operation you can run on top of the RDD. It's transformation, and the transformation takes one or more RDDs and create new RDDs from it. Typical example is map operation or filter operation. A second kind of operation is action. And the actions, it takes some action, as the name suggests, on the RDDs. For example, count how many items are in given RDD, or take the first element, and so on. And now the important thing is that RDDs get evaluated lazily, so that you applying change of transformation and it does nothing. It runs in millisecond because it just logged the operation you want to do, and the RDDs gets evaluated only when you call action on top of that. So there is really huge space for optimization. Imagine that you run, for example, 5 transformations. Last one is filtering, and the action is called calling first element. That you want to run some transformation and are interested only first element. So in, let's say, classical approach, you would run first transformation of a whole bunch of data, save it somewhere, second, third, and then you pick just first element. So basically, obviously, if you know what you want to do, there is pretty big space for optimization so that you run the transformation, and once you filtered first element which matches the last filter, you just return it and can stop. And that's not all. Also, as for replication, you don't have to replicate whole data. You just replicate this sequence of actions. It's called lineage. And when some partition of the data is lost, what you do, you take original data or some RDDs which was stored in previous time and recompute the data. So basically, you don't replicate every single change, and the only thing you replicate is lineage, and when some crash happens, the data are recomputed. And it's, again, safe. It shows that this saves quite a lot of time. And not only that, the RDDs are kept in the memory if possible, so it brings really huge speed up. This is the original paper about RDD. It's quite interesting read, so I recommend it to take a look on it. So this is plot from Spark web page, and it's comparison to run some machine learning algorithm for classification on top of the Hadoop and top of the Spark. As you can see, the speed up is 2 orders of magnitude. It's a really huge speed up. I'm not saying that for every application you have, the speed up will be 2 orders of magnitude. Papers report that usually the speed up is 1 order of magnitude, and for iterative algorithms, it can be 2 orders of magnitude. But again, it's really nice speed up. So I think this is quite impressive and really worth to think if your application can be pushed to the Spark and you can take benefit from it. So it sounds good, but can we do even better? At least for, I believe, at least for some application, yes. Let's try to do the processing of the data once it arrives. Maybe it's quite trivial, a suggestion, but if I ask how many applications really do that, I would believe that not so much, or not so many. And maybe it sounds trivial, but the implementation could be a little bit tricky. But again, fortunately, somebody already did that. And for example, Spark provides streaming, support for streaming. And as the data comes, it creates from incoming data RDDs and put RDDs into micro batches. And emits this micro batches to Spark workers which do the processing. User can configure how frequently the bunch of this micro batches should be created. It has some advantages, but also some advantages to do this micro batching, but usually works pretty well. So if you have some, again, it's immutable, so from, this is, for example, when you have incoming stream, or, sorry, in Spark terminology, it's called discretized stream or dstreams. So here you have incoming stream of lines of the text and some micro batches. And imagine you run this transformation on top of that you split every line into single words and create a flat map from it. So what it does, it again creates new dstream and applies this transformation to every single batch, and so you will get new stream of these micro batches which you can process. So if you rewrite your application to Spark, switch to Spark streaming is pretty trivial. You just do some couple of changing, like changing context to streaming and switch from RDDs to D streams, but internally these D streams again contains RDDs, so there's not so much work to switch to streaming and do the processing of the data in real time as the data comes. If you are not happy with my, yeah.
What happens if there is so much data coming in that you cannot process in real time?
Okay, you probably have to scale your solution or add more brokers.
Maybe during the day there is a certain time when there are lots of, I don't know, borders or news or whatever.
Yeah, but it's the advantage of running your solution in the cloud. So, for example, if you run it on some Amazon, you just pay for what you really use. So during the day, you will scale and bring or create a really huge cluster, and during the night, you can slim it down to one node. So basically, this is really advantage to run it in a cluster. So basically, application have to be prepared for it, so have to be scalable. And Spark definitely is. There can be some other challenges like that if you hardcode something here, so it can happen that this wouldn't be enough and you would like to switch, for example, to 1 millisecond. So this is one of the disadvantage. So here's my answer. Maybe you can switch to some real-time streaming processing frameworks. Probably three most well-known is Apache Storm, Flink, and Samza. All of three are pretty similar. Originally, I wanted to give some introduction to Apache Storm, but I found that I don't have enough time for it. So fortunately, you won't lose the information because it's homework for you. And once you go home, first thing you should do is to open the web page and read and learn some Hello World example of one of three. All of three of them are pretty similar, so it's fine to read, for example, some Hello World for Apache Storm and to have some feeling how it works. It's not something super complicated, so it shouldn't be a big deal to understand how it works, but it's pretty powerful. Okay, and can we do even better? So at least in some cases, I believe yes. And what can we do more? Okay, Spark keeps the data in memory during the computation. And, you usually don't store the data, run some Spark analysis on top of that, and then finish and throw the data away. Usually, you have a whole stack of applications, incoming data, for example, some Spark processing, and the result of this analysis is just resent to another application which does something else. For example, it can be some other processing of some already prepared data, and this application send it further to another application, which can be, for example, some business rule processing engine, which can take some automated actions based on this data, and so on. So there is usually a whole chain of application, and you have to exchange the data somehow between this application. You usually store it somewhere in Cassandra or some SQL database and so on, but let's try to keep it in memory all the time. So how can you keep the data in memory all the time during processing the whole application stack? The answer is to use some caching. Caching is some sketch how cloud works, and you see that caching is a basic principle how cloud works, because it's basically just caching. But to be more serious, the answer is to use some in-memory data grid. like, for example, Infinispan. It's pretty major in-memory data grid solution. I won't come into the details because first, I don't have time for it. And secondly, there was a dedicated presentation about Infinispan this morning. So if you miss it, I really recommend you to take a look on the presentation on YouTube, or if you just want to have some quick review, go to infinispan.org and check some features. I'll just quickly mention that it's no SQL key value data store, but you can also define some scheme. And if you define some scheme, you can run indexing and queries on top of the Infinispan. So this, to some extent, address the challenge which I mentioned at the beginning of the presentation, that you sometimes need some solution which is able to store no SQL data, but at the same time able to store some structured data and run queries on top of that. Infinispan could be pretty good solution for this. Of course, it's scalable, elastic, and so on. There is no single point of failure, so if some node dies, data are replicated and everything works well. One nice thing is it supports transactions. So if you run some, for example, financial application and really needs to be sure that data arrive where it should, it also supports transactions and have quite a lot of nice features. I will talk about some of them a little bit later, but most of them, please go to the infinispan.org or check the presentation of my colleague Jirka Holuša from this morning. So how we can connect it to Spark and things which I talked before. There's a connector for Spark which connects Spark and Infinispan. What does it mean? It means that you can pretty simple, just by 2 lines of config, read and write the data from and to Infinispan from Spark cluster. So here is just that you define some Infinispan server address and name of the cache which you would like to process, and simply create RDDs or stream from Infinispan data. And maybe you can have some different use cases that, for example, data are coming from Kafka, are processed from Spark, and you just want to push the data for processing to Infinispan, so you can, of course, write the data. One nice thing I like to mention is that you can transform RDDs by using Infinispan queries. So imagine, for example, that you store some users into the cache, and now you are interested in only users which has the same name as I have. So you call the query on users having name equals to Vojtěch, and then you filter RDDs just by running Infinispan queries on top of this of RDDs. And everything happens inside the Spark. So it's pretty nice.
What exactly you're going to store in the memory?
Pardon?
Cache in the memory, because we talked about in-memory computing, right? So you want to process your cache and your index in the memory?
Yeah, everything is kept in my memory. Pardon? Oh, yeah. The question is if everything is kept in memory. So the answer is yes. Actually, in Spark, you can define some storage levels. So actually, in Spark, you can keep it also on disk. But what is highly recommended is use storage level memory only. Maybe you can run into some troubles if you use this option, because it can Spark can run out of the memory. But it's, yeah.
Just one technical question. At which point you stop using this memory consumption or technology limits? Because the problem is when the value of data will exceed the cost of processing the data, or vice versa.
It depends on you. So you can store it also today on disk, but basically, if I remember correctly, Or you can use another strategy, memory and disk. So Spark automatically tries to keep the data in memory, and if it's not able to keep it in memory, it starts storing the data to disk. But you have two solutions. You can scale up and add more Spark workers, and if it's too costly for you and you don't have to have the data right now, so you can store it to the disk and process it later from disk. But it would be a little bit slower, but will you cost less money? So it depends on your use cases and how you evaluate your application. But basically you have both options. You don't have to do any compromises.
Did each Spark node come with an Infinispan?
No, but it's recommended solution. Recommended solution is to run on every, or you have machine where you run Spark worker, and recommended approach is to run on the same machine Infinispan or one node of the Infinispan cluster, because the connector is clever enough and it loads only the data which are stored in this Infinispan cache segment which runs on this machine. So basically, yeah, it's not just that Infinispan and Spark shares the same memory, it's load over the wire but over the local host, so it should be pretty fast. So it's recommended solution to run it on the same node. It's not mandatory, but of course, if you would run it on the different machine, you will have latency on the network. But the recommended solution is to run it on the same machine.
But the data will be existing only once in Infinispan.
Yeah.
Not in Spark and then also in Infinispan.
Actually, both, because then.
You double the memory, basically.
Yeah, for processing, yes. Because, yeah. The question was if the data lives only in Infinispan or if I double the data by, if I load it into the Spark. Unfortunately, yes, because these are two different processes which doesn't see the memory of second process. So you have to load in, so yes, but there's some assumption that not of whole data will be loaded into the Spark. So let's say there is assumption that Infinispan will play as more permanent storage, and you will only load some, let's say, stream part of the micro batches into Spark, process it, throw away, and so on. So you don't have to replicate whole data which are kept in Infinispan. Okay, so a couple of other interesting Infinispan features which can be used for pushing the data. So imagine that Spark processing is done, the data arrived, and you like to push it to other application down the stack. So there is pretty easy solution for that. Infinispan has client listeners, so whenever anything changes in Infinispan cache, it sends you the notification that something has changed, so you can take immediate action based on it. Some little bit more advanced concept built on top of that is continuous query. Imagine that your user runs some query on the data you get from your analysis, and once as the data are coming, he wants updates. So you have to open, for example, WebSocket and rerun the query again and again. But with continuous query, you just registered the continuous query, and when some data arrive which matches the query, you are notified about the change and can immediately show the change to the end user or some other application and whatever. And another nice feature is implementation of distributed streams. It's basically implementation of Java streams, but over the distributed data. So if you have some application which only do, for example, some map and reduce, you can avoid use Spark and run it directly on Infinispan. So in this case, you would completely avoid doubling the data. But of course, Spark provides much more functionality because it's a dedicated tool for it. But for some more easy or simple use cases, this would be to use only the Spark. So where we do get from the big data? We try to keep the data in memory all the time, which should speed up processing of the data and exchanging data between the applications. You process the data as they arrived, and results are pushed to the users by immediately as we have it by, for example, continuous query. So can we call it fast data? Well, I don't know, because DevOps Borap stopped tweeting several years ago, so I have no definition for fast data, but actually I think it doesn't matter how you call it. If it makes you happy to call it fast data, let's call it fast data, but what really matters is if it makes your user happy. And if your users are happy, you will be probably happy too. And I believe that applying these techniques will make your users more happy, and this is what matters. I'm not saying that it's a silver bullet which fits to all use cases, so it's just a couple of thoughts how you can do better, and now it's up to you to think about your application and to do the decision if you can somehow benefit from it. If yes, the tools are ready, so just try to use them. So I have only not so much time, so I have some demo. It's really hello world example, really trivial. I will probably run through the code very quickly because I don't have much time. But you can download the presentation and go to my GitHub, and the code is there, so you can go through the code. It's well commented, and it's really few lines of code, so you shouldn't have the problem to understand it. It basically tries to show you or imagine that you have some network of sensors which measure temperature, send it somewhere to some gateway which stores the measurement into Infinispan. Then you want to compute average temperature for every place, and you would like to push the result to the user. So basically it does nothing useful, but it's again a hello world example. So as every hello world example in a cloud, it has unfortunately several components. So the first one is the Infinispan server. It will store all the data incoming and outgoing. Then there is one application which simulates this network of sensors. It randomly generates some capital city in Europe and randomly generate the temperature and send it to the Infinispan. Then there is Spark for processing the data and computing temperature average for every place. And then there is some client application. If I want to be really in a cloud, I should have Infinispan cluster and Spark cluster, but let's skip it for now. Oh, sorry. So I'm starting Infinispan server. My Spark server is already running. So where do I have it? It's here. So you can see I have one master and one worker on my local host. Everything runs on my local host. So Infinispan is running. So now I will start generating the temperatures. As you can see, it generates some random city and random temperature. I will also start my client. Here I'm passing some arguments to it that I'm interested in temperature only in Prague and Vienna, for example. So I don't have all the changes. So now it waits if it gets something. And here I will start Spark streaming, and it will listen to Infinispan and process the data as they arrive. It prints how many data is in every bunch of the stream. So it's gonna generate it around 10 items. So let's take a look. And here you can see that I get updates for Vienna, Prague as they come. So yeah, it's changing. So let's take a little bit look on the source code. Here is the client. As I mentioned, it's just simple cache listener for Infinispan. So the only thing I need to do is to add this annotation that cache entry data created or cache entry data modified. And that's all. And then I can implement my logic, which does only check if the city which is updated is among watch cities, and if yes, it will print something to output. And as for Spark application, it's similar, simple. It just registered to Infinispan and create Infinispan D stream from it, then does some processing like extracting the city and the temperature. Then it, as I mentioned in Spark, everything is done in micro batches. So it can happen that you will get several measurements for a same place in one micro batch. So you group it by the key, and then you just recompute the average with some math function. And obviously, as it's stream of the data, so I need to keep somewhere the previous state. So I will keep number of measurements done during the whole period and some of the temperatures, and from it compute the average. And I need to keep it somewhere. Fortunately, again, Spark provides nice feature for it. It's called state. So you can run the map with state, and it's here. So I'm storing for each city, I'm storing this sum. And what I basically do for every measurement, I update the sum here and update the state. And from this update, I compute the average and return it, which create new stream, new D stream in Spark with averages. And later on, I take this stream of averages and create it back to the Infinispan, which store the data and fire my listeners in another application, which will print it to standard output. So that's simple. Again, I'm sorry, I'm running out of the time, so please check my GitHub, and you can go through the code if you want more. So what to keep in mind, again, try to think if you can if you can keep the data in memory all the time, if you can process data as they arrive, if possible, keep the data in application during the whole memory, processing the whole application stack, and Infinispan and Spark provides really nice features which you can use. So these are some thoughts you can think about, and if you have any questions, I prepared some with answers, but if you have some other questions, so we have a couple of minutes.
Thank you. I would like to ask what's the structure of the RDD when I have Infinispan to store the data? There are just keys to the Infinispan. So if the RDD is transformed, so it doesn't transform with the data, but just the keys?
No, it contains key and value. So pairs of key and values for RDDs, and for stream is key value and kind of type of operation. So if the data was removed, updated, or created.
So with the operation, the data are stored, all data for the transformation are stored into Spark?
Actually, for transformation are not stored anywhere. Data are processed only when you take some action on it, and then are stored in Spark memory. And if you want, you can store it back to the Infinispan.
Thank you.
Okay.
Okay, I would like to ask, how is it guaranteed if I have multiple instances of Spark and multiple nodes of Infinispan, that every single item is processed only once, because I have replicas in Infinispan. So how it's guaranteed? It's
by primary owner of Infinispan. So basically, you take only from primary owner. If it's not available, it talks to the replicas, but basically it takes only from primary owners.
Thank you, Vojtěch, for a great presentation.
Okay, so thank you. If you have other questions, just catch me here in the lobby. Thank you. No, nějak. Jo. Tak, nejdůležitější. To je vymluvený hlas. Já myslím. Oh, okay. Hey.